All right, welcome. If you're just diving into IB physics, you've come to the right place. This is your first and, honestly, your most important toolkit. We're going to break down the language of measurements in mathematics. The very tools physicists use to describe the entire universe. So let's get right into it.
So this is really the big question, right? How do physicists describe the universe with precision? See, physics isn't just about looking at things. It's about describing what we see with incredible accuracy. You should think of it like a language. In this first unit, this is where we learn its most basic grammar and vocabulary.
Here's the game plan for this explainer. First, we'll start with the foundational units. Think of them as the alphabet of physics. Then, we'll cover how to handle the numbers themselves. After that, we're going to tackle the absolutely crucial idea of uncertainty, because no measurement is perfect. We'll add direction into the mix with vectors, and finally, we'll see how all these tools come together to make you a real physicist.
Okay, let's start with the absolute fundamentals. I love this analogy. Just like you can't write a sentence without knowing your letters, you can't describe a single thing in physics without these core units. They're the bedrock, the non-negotiable starting point for literally everything else we're going to talk about.
And here they are, the 6 fundamental SI units you've got to know. Everything, and I mean everything, you'll measure in this course, from the speed of a car to the charge of an electron, is built from some combination of these 6. They are the Lego bricks of physics.
So if those 6 units are the letters of our alphabet, then what we call derived units are the words we build with them. We just combine the fundamental units in different ways to describe more complex ideas.
And this is a perfect example of how that works. Take the Newton, which is the unit for force. Now, it seems like a basic unit on its own, but it's not. It's actually a kind of shorthand. It's a derived unit built from kilograms, meters, and seconds. So you can see how even a big concept like force is really just a combination of those fundamental letters.
Okay, so we've got our units, the letters of physics. Now we need the vocabulary. The rules for how we write and handle the numbers that go along with those units.
Physicists are always dealing with the insanely large, like the distance to a star, and the unbelievably small, like the size of an atom. Writing out all those zeros would be a nightmare. So this slide shows the 2 super clever ways we get around that: scientific notation and metric prefixes, like kilo for 1,000 or nano for a billionth. Both of these are totally essential for keeping things clean and efficient.
Now, let's talk about something that trips up a lot of students: significant figures. Look, this isn't just about rounding your numbers. It's really about being honest. The number of sig figs you use tells everyone who reads your work how precise your measurement actually was. So it is absolutely crucial that you follow these 4 rules to the letter.
Let's see these rules in action. In the number 809.0, that 0 at the end is significant, and that's because there's a decimal point. It tells us we measured all the way to that 10th of a unit. So that's 4 sig figs. But in 0.002, those zeros in the front, they're just placeholders to show us where the decimal is. They aren't part of the measurement itself. That means we've only got 1 significant figure there.
And when you start doing math with your measurements, your final answer can't be more precise than your least precise measurement. It just wouldn't be honest. So for adding and subtracting, you look at the decimal places. For multiplying and dividing, you count up the total sig figs. It's a simple but really vital rule for keeping your science legit.
Okay, let's get real for a second. No measurement is perfect, not a single one. Every measurement you ever take will have some uncertainty, some level of doubt. And understanding and even calculating this doubt is a huge part of experimental physics.
Now, there are 2 main culprits for this doubt. You've got random errors, which are just unpredictable little fluctuations. You can make them less of a problem by taking an average of a bunch of measurements. But then there are systematic errors, and these are sneakier. There are consistent mistakes, like a scale that's badly calibrated and adds 10 grams to everything you weigh. Taking more measurements won't fix that.
So what happens when you use these uncertain measurements in a calculation? Well, the uncertainties combine, or propagate. This table shows you the rules for how it all works. And notice, the rules are different. When you add or subtract, you just add the absolute errors together. But when you multiply or divide, you have to add the percentage errors. That's a key difference.
Okay, theory is great and all, but let's actually see this stuff in action. We're going to use those rules we just saw to figure out the uncertainty in a classic physics experiment, measuring g, the acceleration due to gravity, using a simple pendulum.
All right, so the formula to find g uses the pendulum's length, L, and its period, squared, t squared. That means we've got both an exponent and division to deal with. Following our rules, first we handle the exponent on t. We take the fractional uncertainty of t and we multiply it by 2. Simple. Then, because the formula has division in it, we add that result to the fractional uncertainty of the length, L. And after all that math, what do we get? We find that the final percentage uncertainty in our calculated value for g is about 2%. And listen, this number is just as important as the answer for g itself. This is our statement of confidence. It tells anyone looking at our work just how good our experimental result really is. So far, pretty much everything we've talked about only has a size, or what we call a magnitude. But for a lot of things in physics, that's only half the story. I mean, what about force or velocity, where the direction is just as important as the number? For that, we need a new tool. We need vectors.
This slide nails the core difference perfectly. A scalar, like speed, is just a number, say 60 miles per hour. But a vector, like velocity, has both the number and a direction, 60 miles per hour north. And believe me, that distinction is absolutely critical.
Here's the thing. You can't just add vectors like you add regular numbers. The easiest way to picture it is the tail-to-tip method. You draw the first vector, and then you draw the second vector starting from the arrowhead of the first one. The total sum, what we call the resultant vector, is the one that goes from the very beginning of the first one to the very end of the second one.
A lot of the time, the easiest way to deal with a vector mathematically is to break it down into two perpendicular parts, its horizontal part and its vertical part. Using a little bit of simple trigonometry, we can resolve any vector that's at an angle into these two components, and that makes them way easier to add up when you're solving a problem.
So let's wrap this all up. We've gone through units, numbers, uncertainty, and vectors. Each one of these is a totally essential part of the complete toolkit you're going to need to think like a physicist.
And here it is, your starter kit. You've learned the fundamental language of units. You know how to write and do math with numbers honestly and responsibly using scientific notation and sig figs. You can actually calculate your confidence in an experiment with uncertainty analysis. And you can describe things that have direction using vectors. You've got the tools.
You now have the foundational language of physics. And this isn't just a bunch of rules you need to memorize for an exam. This is a seriously powerful way to ask and precisely answer questions about how the entire world works. So now that you've got the tools, what do you want to find out first?